Let's consider the function y equals f of x equals 2 minus x squared. And let's assume this function is defined on the interval 0 less than or equal to x less than or equal to 1. We want to find the integral of this function on that region, and we want to represent that graphically. So our function is fairly easy to graph. It's going to look something like this. It's going to be a parabola centered at the point 0, 2 up here. It's going to come down to an altitude of 1 when x equals 1. And the integral can be thought of as representing the area between this curve and the x-axis. In order to construct the integral of this function, we first consider an interval of the x-axis, an interval of length delta x, and we're going to consider that we have a sample point x star within that interval. Now let's enlarge that slightly. So let's represent our interval delta x here. Our point x star, which can be any point, randomly chosen point within the interval, any point within the interval. Now we're going to consider the case when delta x is small. Now the delta x that I've actually drawn here is pretty big compared to the interval between 0 and 1, drawing it bigger than it would actually be thought of. Okay, so delta x is going to be considered to be very small. But for the purposes of illustration, we make it a little bigger. So if delta x is small, then the region beneath this graph is pretty close to a trapezoid. Even this region is pretty close to being trapezoidal, and the area beneath the graph forms something very close to a trapezoid. So I'm going to represent the behavior of this function as a trapezoid. As you know, to get the accurate area of a trapezoid, and we might want to do this if we're trying to approximate the integral, but if we take the midpoint of this trapezoid and level it off, we get a rectangle whose area is equal to the area of the trapezoid. In this case, we're going to use the sample point x star, and we're going to evaluate the function at x star. Now that value, and it looks like I've kind of missed my point here, but we get the idea, will be the graph altitude up to this point, the point where the graph of f of x meets the line directly above x star. In other words, the value of the function f evaluated at x star. So the area equals f of x star delta x, our approximation to the area beneath the graph. Of course, we would have been better off to choose an x star maybe closer to the center of the interval, but since, as you know, we're going to let these intervals have widths that approach 0, our sample point x star is, as we take limits, going to have very little room to maneuver, so that as the width of the interval approaches 0, the values of x everywhere on the interval become arbitrarily close to the value of x star. And the proportional difference between the values of f of x star and the average value of the function on the interval become insignificant. To construct the integral, we partition the interval between x equals 0 and x equals 1 into a series of subintervals. So we partition. And our partition consists of point 0, which is going to be x0, less than x1, less than x2, and so forth. We'll have some interval, an arbitrary interval, that we consider to run from x sub I minus 1 to x sub I, and so forth, until we come down to the end of the interval at xn equals 1. It's not necessary, but let's go ahead and assume a uniform x interval, a uniform delta x, so that our picture here could represent this ith interval. In that case, the left-hand x coordinate would be x sub I minus 1. The right-hand endpoint of the subinterval would be x sub I, and our x star, our sample point, is going to be denoted by x sub I star, and the area is then going to be f of x sub I star times delta x. That'll be our approximation to the area, and we'll call that delta A sub I, the area corresponding to the ith subinterval of this partition. In the next clip, we're going to consider how to represent the sum of all the areas in all the subintervals, the sum of all the areas corresponding to all the subintervals, in other words, the total area under the curve, as approximated by this process.